try to implement the second method. The second method is a optimization method that can be used to minimize a function with just one variable. So let's first take a look at the second method. So we are going to generate, starting from the initial guess, x0. You can generate a sequence of points using this way. The xk plus 1 is equal to xk minus this bunch of thing. And then you can simplify the right-hand side. Eventually, you get this. So we want to implement it into steps. So this is the formula lecture 1. The first slides, the first set of slides for from the course website. Okay, so we are going to implement this method. So I'm going to write a note at the beginning to comment that this file is about the second method. Okay, so everything I write inside this triple quote are comments. So I can write multiple lines if I like, but just going to write it in that way. Or you can use this second method right in this way, and everything after the pound sign, this line, will be comments. So if you start with this pound sign, they will just give you a comment. This line will not be executed in Python. Okay, so you can create this file. I forgot to say that you just create a blank plain text file. You can use the Notepad or any text editor. Just to create a pure plain text file and then name it to the whatever the name you want. I call this one secant.py here. You can call any name you want, and just remember to have this .py as the attribute. So this means it's the Python script. And then I'm going to import the necessary packages. To import numpy as np. So numpy is a package that contains many useful functions. To use a lot in this class. Now we put it as a shortcut np. So in the future, I can just call the np dot something to call the function inside. And then I'm going to define this second method. So as we can see from the method, we actually need two initial points, x0 and x1. We start from this, and then we need to evaluate. We need to know how to evaluate the derivative of a function at any given point. So this f, or derivative of f, is actually something we need. We're going to specify that later, but at the beginning we need this x0 and x1 as our initial two values. And also I'm going to specify the maximum iteration number. I set to 100 as by default, but you can set it as other values as well. You can set the tolerance to be the relative change of your iterates. So let's say I set it to 1, -3. So this is default value. When I really call this function, I can use other values as well. Okay, so here I'm going to implement this algorithm. So I need to run this loop for I in range max iter. So what this is doing is that the I will go from 0, and then 1, and then 2, up to max max number of iteration that you set here, -1. So actually I can do this. I is from 0 to this. They will go through, in this case, will go from 0 to 99. But if you start from 0, you don't really need to write this one here. In case you want to start from 1, that's fine as well. But I'm going to start from 0, which is the starting index for in Python. If you use MATLAB, they will always start from 1. Okay, so now I'm going to compute the next point based on the 2 points I just I have. And, this line should be written as. So let's say the numerator that I have the new x should be equal to this difference. The numerator that I have is this, xk minus 1 and xk. So now let's say this is my x0, this is my x1, right? And then this I have the df of x1 and df at x0, and then on the denominator I have df dx1, dx0. Okay, so I'm going to have the x0 times df at x1 minus x1 times df at x0. Okay, so this is my numerator. So remember that for the given x0, x1, I can do the computation like this, and the denominator will be df x0. You know what? Let's compute that just for once. So this is df at x0, the y0, y1 equals to df at y1 or yx0. Sorry. So now I have this, which will be y1, it will be y0. So now what I wrote here is that I will assign, I'll compute the value of df, derivative of f at x0, and assign this value to the variable y0. So the y0 will take this value on the right, and also y1 will take the value right here. And I can compute this. Then we'll have the y1 minus y0. So let's check if this is correct. The y1 minus y0 on the bottom. Okay. So this is my new x. This will be my new x. And my new y will be df at x. Okay. So now I'm going to check if this x is making sufficient progress. What I mean by that is I can check if the difference between x and the previous x1 is small enough. So I'm going to compute this value. I think I need NP. So just taking the absolute value of x minus x1 and divided by, there's x1 here, or you can divide it by x if you like. So this is calculating the relative change that you made. And you see if it's lower than the tolerance you have. If it's lower than that, that means, let's say the error we set is this. If the relative change is less than 0.1%, that means it's not making too much progress. So we probably want to stop. We want to break out from this I loop right here and output the value. Okay, so if that's the case, then you can just break. But otherwise, you're going to update your x and y in the next loop. So in this case, you have to call the x0 to be the previous x1, x1 to be the new x you got, and the y0 to be the y1, and y1 to be the newly computed y there. Okay, and then you can return the value of x, which is a minimizer. So after this loop, you will reach to the maximum iteration number, then you can terminate the computation and return the x. And in this case, as you can see, the first iteration, you will do this x0, x1, do this kind of operation. And this x will be the x2, and this y will be the df f prime at x2. And then you'll go back to this loop for I equals to, for the next iteration, I equals to 1 in this case, because the I start from 0. But it doesn't matter, I is just a counter. So in the next loop, you will do the same thing. But since you updated the x0, x1 values, and the y1, y0, y1 values, so it will change this x0, x1 to x1, x2, and then do this computation, to this kind of computation. So then you have the x2 here, and then you update x1 to x2, and then you can repeat this computation. So this is how the loops are formed. Okay, so you can return the x. Okay, so that's pretty much it for the second method. You can test it out. You can see that I'm trying to minimize this function f x. I can define my df to be, let's say, how do I minimize a function of, say I want to minimize this function, right? X equals to x squared. Okay, so I put this as comment because I don't really need this f. I just need the derivative of f. So the df x should be just 2 times x, right? And then so I can define my df to be x, df function to be just return the value of 2 times x. Okay, so this is the definition of my function. So essentially I use this df, which is derivative of this f, and I'm trying to minimize this f right here. So I know that the minimum value will be 0. Okay? So the x should eventually after taking the second method, it should give me 0. So now let's call this function secant and return this x value. So this is secant. This is the function name that's just defined right here. I need to take those inputs. So I need this df, which is the one I just defined here. And then I need to give 2 initial values. So let's call them, say, 0.1, 0.2. If you like, I can call 1 or 2 if you like. Just give 2 a random initial guess. And then you can also set iteration number. Let's say just set to like 50 iterations. And then I can set this to e -2 if I like. Or if I just skip that, I will take this value, default value right here. I'm going to do this. So let's see, and I'm going to print out what is x. Okay, so let's save the file and go to terminal. So let's see. So I put the file right here under my downloads folder, and there is a secant.py file. I'm going to execute it using the secant.py. Okay, I'm going to do this. Some error here. Let's see where the error came from. It divided to 0. Okay, so let's see. Go to make this slightly larger, and then do that again. Oh, it's again 0. So let's maybe not minimizing this x minus x squared. Let's say x minus 1 squared. In this case, the derivative will be 2 times x minus 1, and then I have 2 times 1 here, and then let's say I start from 2 and 3. Let's see it again. Okay, so it's returning the correct value right now. It's the minimum value of this x minus 1 squared is x equals to 1. Okay, I can try other things if you like. But this is pretty much what this second method is doing. I can remove these 2. I just need to give 2 initials. Yeah, like that. Like it, so that'll be the second method. Okay. So this is just implement a very simple algorithm, but we eventually need to use the line search. I use this function as a line search. So I'm going to save this. It's not necessary. So I'll need to implement the line search later on. Okay, so depending on which method we're going to use next, say let's use the steepest descent algorithm. Means that I use a negative gradient as the search direction, and then I take the line search to find the step size. So the line search part will be the second method right here. Okay, so now I'm going to implement the line search, the steepest descent. Okay, so let's define a new function called steepest descent. And in this case, we're dealing with real problems, and the f that we have will be multivariate function. So I'll take vector as input. And what we need to do right here is that the f I need, so this f will be actually the function. So let me call it a different name, the fun function, and then the grad of the function, and the x0, which is the initial, and then also we need the maximum iteration number. Let's say I set to 100, and also the tolerance, I set the tolerance to 1 negative 3 as well. Okay, so now remember what we need to do with this steepest descent method. Let me pull out the slides. So the steepest descent method is this. Close this off. Okay, so steepest descent is doing, say, right here, the gradient descent or steepest descent. So this is the gradient descent. So you have the given initial x, we compute the gradient, and then that will be the g there, and then you update the iterated in this way. So the xk plus 1 will be equal to the previous xk and minus alpha k times the gradient at the previous xk. It's right here. The steepest descent is to find this alpha k to be the minimizer of this line search function right here. So we need to find this for given the negative gradient direction as the search direction, and we find this alpha so that I can minimize this. I'm going to use the line search method, which is wrote. And let's see. Yeah, so that's pretty much it, and then we just need to implement this step right here. Okay, we need to find this alpha k to be this. Okay, let's go back. So what we need to do right here is that I'm going to start a loop again for I in the range of max iteration number. I'm going to remember that I need to compute the gradient. So let's call the g equals the grad of x0. And then I will need the set the descent direction. Let's say I just set my descent direction to be negative g. Okay, so remember for a given value of x0, you compute this gradient vector, and then my search direction is just negative g. And then I need to, the most important part is I need to figure out the line search function. So line search function, it try to minimize the gradient. Let's see, we try to minimize this. So as you can see, this is a function of alpha. The alpha is a scalar. This is a function of alpha, and it will return a scalar value function. So the function will get input alpha, which is a scalar, and output a scalar. So if we want to minimize this, or treat this as a function of alpha, then we need to take a delta with respect to alpha. We get when we use the chain rule. Let's see, where I think I should have it here. Yeah, it's actually here. When you take the gradient of this, I think I have this slide here. Essentially, what we're trying to do is this, right? Because we defined our, so right here. So we defined our phi to be this, so the gradient of phi should be this. Okay, I'm going to implement this step. And as you can see, this is just evaluating the gradient of f at this x minus alpha g. So for every given alpha, I should have this value as a vector, and then I have this g. So let me just implement this step right here. Okay, I'm not going to have this line here. I'm going to just define my derivative of the line search function to be, so d of line search function should be equal to the gradient I just computed and the gradient of this x0 minus some alpha, I call it a here, and then this g. So after I compute this, it should give me a vector, remember that. And then I also already have the g here, so I need to make the inner product of them. This np dot. This is the mapping a matrix multiplication. The g is a column vector, and this will be giving me another column vector. So this dot t is a transpose of that column vector. It becomes a row vector. So multiply these two and give me a scalar. Okay, so this is I define it, but I have to really define in this way. So I need to define this function for any input a. Is going to return me this value. Okay, so this is I define this function inside the steepest descent. Now this is line search because this changes every time. For every new iteration, I'm going to have a new phi function, and the derivative of this phi function should be like this. Okay, so that is the line search function, and then we can find the optimal step size. Step size is the secant method. We'll apply the secant method to this d line search function. And also I need to give two initial values. Let's say I always set to be 1, 2, and the maximum iteration number I always set to like 220 iterations, maybe, or 30 iterations. And also this e-2, say. But if you do not specify these two last values, they will take these values right here. Okay, so that's all we need. We need the derivative of the function, the 1 and 2 as the initial two initial points. So what we're doing here is that we're applying the secant method to this function, but this function is defined right here. So let me pull out, maybe I pull out the other. Another one right here. Let's see. Yeah, maybe I do it here. Okay, so remember that when we do the line search, we need to find the phi alpha, and then we need to minimize this phi alpha defined in this way. And this d in steepest descent, d is always negative g. But for a conjugate gradient or quasi-Newton method, we need to specify this d otherwise. And then the derivative of the phi. So this is actually the derivative of the line search function that we implement. That we need to serve this into the we need to put this into the secant method. We need to ask the secant method to compute the minimizer of this phi, and for that we need to give the lines. We need to give the secant method this derivative of the phi function. So this is actually what we had just did. We have okay, then I have this step. So then we'll compute this new step right here, and then the next step would be just to update the x to be the x0 minus step size times the g. Okay. So that's the iteration that we have. Right? That's the iteration we have. We need to implement this step, and this is essentially how we update the new x. And then we can check. So again, similar as before, we can check if we're making sufficient progress. And if it's less than the tolerance, then we will just break out this I loop. Otherwise, we'll continue and update this x0 to x. Okay, and I think that's it. Okay, I think there's nothing else. And if you want to be fun, let's do it later. If you want to be fancy, we can print out the value every time. But up to this point, we should get the after finishing the loop, we should get this x, return this x value. Okay. So let's see. We can try it out. Try it out. So let's say we have an x. Let's say we want to minimize a function from the class. We need to just search one. Maybe this function. We'll try to use the steepest method for this. And the function looks like this, right? And the gradient of this, the function is like this. So I'm going to define the function that I'm trying to minimize. I'm going to define this f. For a given x, it's going to give me this thing right here. So I have to compute this for each given x. Let's say x1 is the first component of x item. So this is just to make sure that if your input x here is a matrix or a vector, sometimes when you just write it in this way, it will give you a vector or matrix, which is not, it's just the first component of that the matrix or that vector, but they still put it as a matrix. So I'm writing this just to extract the actual value from out of it. So it's a little bit stupid, but this is how Python does. If you're using MATLAB, it doesn't have this issue at all. Good to have this. Also, the starting index is always 0, so it has 3 components. And, they are actually the 0, 1s, and the second of this vector. And then with this, we need to get this x minus 4 to the 4th, x2 minus 3 to the squared, and then that. So let's see. So the y value will be x1 minus 4 to the 4th plus x2 minus 3 squared. So this double star means the square. The single star means the multiplication. And the 4 times x3 plus 5 to the 4th, right? Yes, so everything is correct. Okay, I have these terms, and I'm going to return the function y value. But I'm not just, I don't need this f, I also need this derivative, right? I also need the df. So let me call this function, call this gradient of x. So I'm going to do the same thing to extract the actual values. And then I will need to compute the gradient. So the gradient will be a vector. I'm going to get the gradient to be 0 and p dot zeros of 3 by 1. So this is giving me a 3 by 1 vector filled by zeros. And then this g1, g0 will be equal to the derivative of this function with respect to x1. So that'll be derivative here will be 4 times x1 minus 4th cube. Okay, just make sure that's correct as I want. This G1 goes to 2 times x2 minus 3. The G2 will be, the derivative of that will be giving me 16 times x3 minus 5 plus 5 to the cube. Let's again put the parentheses. So that's this one that we just wrote. Okay, so now I'm going to return the G. Okay, so once we retrieved the function values, the x values, I'm going to construct this G, which will be my gradient. And this is the G that I need to supply to this steepest descent method. So now since we already have this function f and g defined, let's also specify the initial value x0. So let me say the x0 is an array say the array it started from 4 to -1. So it's 4 to -1. So this is giving me an array in NumPy format, and I want to reshape it to a column vector. So this x0 into a 3×1 vector. I reshape it into that way. So now every vector will be column vector in this part. So then I think I'm ready to go to apply the steepest descent. So x is steepest descent, and I need to supply the function, the gradient, the initial value, and then these two. So let's see. The function is what I just calculated, the gradient. So these two are the functions that is defined right here. This function and the gradient of the function. And also I need the x0, and I can set the initial, the number of iteration numbers, set to 100, or 200, and this to be e-4, say. Okay, so by doing that, it should return the value. Okay, so that's pretty much it for the steepest descent. Let's try it out. So let's again Python. I write everything into the same secant.py file. So I'm going to just segregate this way. See, there's slight error here. Oh, I shouldn't have this absolute value because it's not a scalar. They are both vectors. So I'm going to call this norm function. I'm going to call this norm function. It's under the NumPy package with this LIN algorithm, means a linear algebra. And then within this, there's a norm that can evaluate the norm of a vector. See one more time, and there's arrow. The true value is still on this line. Did I save? Oh, I saved the wrong one. So this is still absolute value. Sorry. This is still the absolute. I need the absolute value. I need the norm here for the steepest descent. Okay, so I think this, yeah. So this is giving me cleared out. Again, Python secant.py. So this is giving me the value after, say, 1200 iterations, or maybe before that, where this iteration is stopped. But as you can see, the result is 4, 3, -5. It's basically the the same as this one, pretty close. And if I want to see the progress in between, I can actually do this. For every iteration, I'm going to print out the value of x and the function, or the x and the function value at x. So I can see iteration d, x is something, and or x1 is this, x2 is this, x3 is this, and the f of x is this. So I'm going to tell what are the values, the percentage g. The first one is the iteration number I. The second one will be the x, the 0th entry. Again, I'm going to print out the value, actual value right here. And also the x1 dot item. So extract the actual values instead of printing out a one-by-one matrix. Okay, again, if you do MATLAB, it doesn't have this issue at all. Okay, I think that's this, and then I will need to evaluate my f at this value, x. Okay, so that's, I have 5 numbers to fill in, and there are the I and x1, x2, x3, and this function value here. So let's see if it works. Let's clear out and run this again. I think, oh, yeah, it should be fun function. So this is actually the input that we need here. Okay, so that's what we want. And at iteration 0, we get this x1, new x1, x2, x3 to be this. And, the function value is right here. And then the second iteration, so on and so forth. So it's actually stopped at the 11th iteration, and probably think that the x is not making much progress. We can make this tighter. So say that I'm not want this, I want maybe 7. I wanted the stopping criteria to be that tighter, a little bit tighter. So if I run this, I will run to, oh, okay, so it will run to actually to the last iteration, and this is the function value. We know the function value, the optimal function value should be 0, because by looking at this, you can see all the terms are non-negative, so the best value will be just 4, 3, -5. Okay. But yeah, okay. So yeah, that's the output. Okay, that's pretty much the steepest descent method. And you can implement the conjugate gradient method. It's just that you need to specify the d. So maybe your d is something like g, -g plus something. And then you can use the d inside. Right here, for example, or instead of using -g, you use d. And also here, you would use the d as a search direction. But otherwise, it will be the same. And the most important part is this line search part, how to find the best, or to find this step size for each iteration. You have to decide, or you have to determine what is the line search function or derivative of the line search function. That's actually just this part. Okay, so that's pretty much it. If you have any questions, just email me or come to my office hour, so you can better go through the problems you have. But otherwise, this will be the steepest descent method.